So today we're going to finish off with an important topic, and actually it's one that actually you need to know a little bit in order to actually solve, I think, one of the problems on this week's homework, and that's our targeted social contract. Is that for a homework due Friday, we cover all the material by the Tuesday lecture. We don't always make it, but that's our goal. That's our aspiration. Okay. So, and then we're going to start actually one of our last theory topics. It's actually super interesting. After we cover this, we're going to jump into duality, which is fun, and we'll do that for this week. That's super interesting, and these are probably things that most of you haven't seen, or if you've seen, it wasn't people describing it didn't use the D word for that, right? So but you will have seen arguments for it maybe in a statistics class or in other classes, certainly in economics. I don't know if they use that word or not there. We'll find out. But okay, all right. So let's go over vector optimization. Now, just to put this in context, we looked at vector inequalities. And a vector inequality, what happens is, something like that is a vector, and this inequality is now to be interpreted in a vector sense. Like this could state that a matrix variable is positive semi-definite. That'd be an example. Now, when we were doing that, we did not change the semantics of an optimization problem, right? The semantics was identical. And the semantics, I'll repeat it one more time, it's this. Semantics of an optimization problem is if a point does not satisfy all the constraints, if it is not feasible, it's completely unacceptable, and there's no more discussion. Okay? Among those that do satisfy all the constraints, the one with this least objective, which is a scalar in a standard optimization problem, is the best one. Everybody got that? So that's the semantics. There's nothing else to it. Now we're going to be talking about vector optimization, and what we're going to do is we're actually going to now generalize not constraints, but the objective to be a vector. Now, there we're actually going to have to mess with the semantics, because what does it mean to say, minimize a vector? Like it offhand, and it turns out it can mean lots of things, and not surprisingly, the main distinction is going to be things like minimal versus minimum, right? Because, well, vectors are generally not, the most orderings you have on them are not linear orderings. Okay. Okay, so this is what we're going to do. So it's going to look like this. And now this one, we can state what it is. That's its syntax. What we have not yet given you is the semantics, right? So I could do things like here would be an example. I could say, hey, please find an estimator. And you go, what's your objective? And you go, make my error covariance matrix small. Everybody got that? That is a problem just like that. Of course, immediately someone would say, what do you mean by small, right? Because then there could be lots of ways to say a covariance matrix is small, right? Oh, one way that would be clear is if there was one choice for which a covariance matrix was actually smaller than all others, otherwise known as a minimum, then it'd be completely unambiguous that's what would have to be the solution of this. Everybody got that? But we'll get into this. This is kind of the idea. Okay. All right. So the first thing we'll do is let's look at the set of of achievable objective values. So what that means is we screen out all choices of x which are not feasible, and we only look at the ones that are feasible. So they're the ones that don't get like an immediate rejection, right? So we look at the ones that are feasible, and then we look at the set of objectives. Now, if this was a scalar, this O would be a subset of R. In fact, it would probably be continuous. So therefore, it would be an interval of some kind, right? And then it's completely simple to say what the semantics is for a scalar op. It's basically the one farthest to the left, which is the smallest, right? Point in that interval. So that would be that. Here, this is like a weird set. Like, for example, let's pretend that this is with respect to r plus to the 2, right? So let's say that here are the objective. What that means is basically down and to the left is good, right? If you take that to be the objective, then it could be that O looks like this, right? And here you see there's a minimum point, in which case you just simply say it's optimal, period. It's just optimal, right? That's what it means to be optimal. Basically, that happens pretty rarely, but it does happen in some very famous examples in, let's say, statistics and estimation, right? But generally, it's not. Okay. It's Pareto optimal is the name that you would give to a point if f0 of x, that's a vector, remember, is a minimal value of this. And so what that means is, like, here the achievable thing. Here's what you can do. Remember, in this one, r plus squared is the vector, is the cone we use to compare vectors, right? And so what that means is if you have a point here, everything to the left and down, these things are better than that point, right? So when we talked about minimal points, we didn't assign like something's better than something. Now we are, because we're doing minimization. And we want that, quote, small, but that means small in this vector sense. So these are the things that are better, right? So for example, there's an x that achieves this value, okay? And I mean, the technical name for that is a stupid choice of x, right? Because basically it's silly. You're so like, look, if you take this thing, there's all sorts of points over here, which actually are unambiguously better than that choice. And this is in the vector sense. Right? The minimal points of this set O are these over here. It's this boundary here, and then that's open, and then this boundary here. So for every single one of those points, there's no point that is strictly better than that point. Right? So these are they're literally the minimal points of O, which is the achievable objectives. And it kind of all really makes, I mean, this makes perfect sense, right? So, and then actually if someone says, can you compare this and this? And the answer would be no. And no one could say you can't say without further information, you couldn't say that that's better than that. You could just, in fact, a very good name, another name for Pareto is a great name. I forget which field uses it. It's called non-dominated. Right? So a non-dominated point, right? Because something like this point here is dominated. It's dominated. In other words, there are choices which are simply better. They're strictly down and to the left, okay? So that's dominated. And the points that are not dominated is this boundary. It's the set of minimal points. It's also these are called Pareto optimal is another name for it. That's from economics, actually, I think from the 1890s. Something like that. This is not exactly new material. Okay, so this is the new semantics of a vector optimization problem. Okay, it's clearest in the case in what's called multicriterion optimization, and this is a vector problem where we just have the cone, and our objectives actually have. So we would literally refer to these as our objectives, F1 up to FQ. Right, those are our objectives. Altogether, they become a vector objective, but literally you'd call these these are the objectives, right? I mean, okay, and let's see what it means. So here's what it would mean. If you have these q different objectives, and basically, roughly speaking, you want all of them small. That's the idea, right? And so if you have a point that's optimal, what it means is it's both feasible, and it says. Basically what that says, that there is a choice of x where it minimizes F1 and it minimizes F2 and it minimizes F3 and it minimizes all of them, right? That's what it simultaneously minimizes all of them. This is an example like this, right? And this says that there was no competition among them. I found a single point that just minimized everything. So I mean, and I should add, this should be kind of obvious, but I'm not aware of any problem in a practical setting that's not a multi-criterion problem, right? Because everything, a lot doesn't matter. You'll see very shortly how to solve them. It's a not big deal. Some people actually make this into a field, which I find ridiculous, because if you know how to do these things, it's extremely straightforward. So any field there are going to be trade-offs among competing objectives, right? I mean, if you're fitting a model in machine learning, you'd have a loss function and you'd have a regularizer, and you'd want to trade off among them, right? In control, you want to hit your target, and you could trade off fuel and the comfort of the ride, right? Or something like that, right? So there's just pretty much any problem I can possibly imagine there'll be, but then they're very easily, as we'll see shortly, handled by straight up optimization. Okay, so anyway, okay, back to this. So this is, I mean, by the way, this happens very rarely, right? If you would say like, oh, I'm doing this circuit design, I care about the area, I care about the power, I care about the dynamic power, and it doesn't matter, that's it. And I care about the maximum power output of my amplifier. There you go. Okay, so I have like 4 objectives. And then you come back and you go, cool, here's a design. You go, well, what does it do? You say, oh, it minimizes all 4 of them simultaneously. Everybody got that? I mean, that would be awesome, right? But this happens like basically never, almost never, okay? Pareto optimal is actually interesting. So to be Pareto optimal, what it means is the following. It means you're non-dominated. Here's what it means. You say, well, I have an X, and you get these Q different scores or objective values. Then what you know if you are Pareto optimal is that nobody can embarrass you, right? Embarrass you means, oh yeah, well, I've got an X that matches you on all and beats you on at least one. Everybody, that was informal, but it was actually a precise statement of what it meant to be Pareto optimal. Everybody got that? Right? So, yeah, so you'd say, well, I know how to do my production, so I'll take your plan for production, and I'll say, yeah, I got a plan. Mine, of the 12 resources that we both use, I match you on all, and I beat you on 2. That means my plan dominates yours, which means yours is not Pareto optimal. Of course, mine need not be either, but that's what it means. Everybody, so I think these are ideas you've seen before. They're very simple and I think intuitive. But I think it's not a bad thing to actually, have it called out with a name associated with it. Okay. So the one thing that people in a lot of areas, when you talk about Pareto optimal, they talk about, you talk about trade-offs. So, which is I think an extremely good way to say it, right? So if you look back over here, remember this is an optimization problem where we're basically optimizing 2 things, right? We want the first component small, right? So left is good. And we want the second component small, which means down is good, right? And then this is and so what we would do is if someone pointed to so that's a stupid choice. That's an impossible choice. Perfectly nice one, but impossible. This is possible but stupid. These are the not stupid ones or the Pareto ones or something like that. And what people they refer to this as like an optimal trade-off curve. And then if you were to choose these 2 points and say, let's discuss, right? Let's compare. And you would say, well, neither's better than the other, right? Because they're not comparable. It is not the case that, one, and then you'd say, well, what happened? And you'd say, well, if I was going to compare this point and this point, what I would say is this point up here beats this one in the first objective, but pays for it with this second because it's higher. Okay? And so and that actually gets you kind of to some economics, a simple economic interpretation where you are exchanging these between the 2 objectives, sort of paying for one with the other. Everybody got, and these are all just vague ideas, but they're about to be not vague very soon. Okay. Okay. So, here's an example. It's a Bicriterion problem with 2 objectives, right? And in fact, this is basically a least squares objective. So this might be this could be your least squares training error or something. Sorry, and then this would be like, if you're doing ridge regression, which we'll get to later, but actually this is interesting. What this does is it says, here's what the semantics of this is someone saying, choose an X, and you say, how will you be judged? And you say, you will be judged by 2 numbers. Number 1, this thing, you want to call that your tracking error, training error, whatever you like, I don't care. You'll be judged by that one number. And you'd say, I want you to please try to satisfy approximately AX equals B. you say, oh, but at the same time, I don't want x to be too big. And that's the second number you are judged by. Okay? And so this is an example of that set O, right? And so what it says is we didn't do it this way because you can actually calculate that set, but it doesn't matter. But in principle, what we did is we took all x's in Rn, we evaluated that number and that number. That's a 2 vector, and I put a dark spot wherever that happened. Everybody got it? And so this is what's achievable. Now, everything up here is ridiculous and silly, right? Because the semantics is left is good, down is good, right? So it turns out the only ones you should possibly ever consider are the, you could say either the minimal ones in O or the Pareto optimal ones or something like that. And that's this little curve right here, okay? Including the endpoints, right? So that's everybody got that? So you would, if in fact you cared only in your choice of x about these two numbers, then it would be extremely silly to choose any choice of x other than the ones on that line, right? And then the way we would say this is we'd say things like, if you wanted to compare, this point and this point, we would say, oh, you just traded off, fitting error with, the size of your parameters or however you want to say it. That's how you would say, okay? So again, this is all kind of obvious, but this is what it looks like, right? Okay. Here's a famous one. So you're doing portfolio construction. So I'll say a little bit about it just so everybody is kind of on the same page. So X, that's an investment portfolio, and it's usually normalized to 1. Actually, this is the case where they're all non-negative and added to 1. So it's actually this is a set of mixture weights, and basically tells you what fraction of your wealth do you invest in each of these things, right? So, and this is used like absolutely everywhere. It's used on a kind of a macroscopic scale, like Stanford endowment sits there. But there, the individual investments are like asset classes, like, US equities, European equities, alternative investments, venture capital has a named, is actually one of the assets in Stanford's endowment, right? So that's this. And then this is asking, how to make a mixture of it. By the way, later we'll talk about it, but you can violate this, right? So, and it has a meaning, right? So you can actually have, and you can interpret the x's as percentages, right? So if I could give you, if I had 4 asset class, this would be like really dumb, but be like, stocks, bonds, and cash, and I could give you like 60, 40, and 0 or something, right? Or something like that. You've heard of these things, right? But in fact, you can actually, in stuff that we'll see later, you can actually let x get negative. And you might ask, that's weird. What does it mean to hold negative 5% of your portfolio in, I don't know, whatever, it doesn't matter, medium-term corporate bonds. Everybody see what I'm saying? So I can explain it again. This is, by the way, all of this for most of you, this is nothing but like cultural enrichment. Just so if you ever bump into someone who is interested in this, you know what they're talking about. So if you do genetics, too bad. Sorry about that. But it's not bad to know these things, right? To know how optimization is used in other fields. Okay, so what does it mean to own negative 5% in, whatever medium-term corporate bonds, right? What it means is you borrow that asset from someone, right? You now have the obligation to pay them back, right? And so you borrow it and immediately sell it, okay? Then later when they come ask, when the investment period is over, they go, hey, give me my bond back. You buy it on the open market. If the price went down, it's cheaper and you did well. Everybody got that? So again, you don't need it, but what's really cool about it is all the math goes through, and so you could actually have, you can own negative, anyway. So yeah, that's the idea, fine. All right, this is just a discussion of this because this is the first time we're seeing this. Okay, so this is sort of a very classic analysis. It's kind of like, although it's got parts of it that were not in the original thing, this goes back to like 1953 with someone named Harry Markowitz, right? So here's what it is. Care about 2 things. So I'm going to make this investment portfolio, and there's going to be a return here. There's going to be a return, and the return on return is like, the return might look like this, right? It might be plus 0.02 minus 0.01, you know, and plus 0.02 or something. And this means asset 1 went up 2%. So did asset 3. Asset 1 went down 1%, right? That's what it means. So, and if you form R transpose X, that's going to tell you the portfolio return, right? So, you know, if you have like, you know, 80% here, 10 and 10, you just work it out and figure out how well you did. And you probably went up about, you got dinged a little bit here. You probably went up somewhere near 2%, but not quite. Everybody got that? Okay, so that's what that, okay. So the model of R is that R is a random vector and will give its first 2 moments. And those first 2 moments are going to be the expected value. And P bar transpose, that's going to be the relative price changes, the returns. That's this thing. Oh, I guess I'm using bad notation here. That's fine. Or inconsistent. Okay, so that's going to be the expected return of the portfolio. And then the variance is going to be X transpose sigma X, right? And so you should have some estimates of what things are going to, you know, the mean and the covariance of these things. Okay, everybody following this? Okay, you care about 2 things, which is you would like a portfolio which on average kind of goes up. So you want high mean return. And a lot of people drop the mean and just say high return, right? So that would be how they would say. Of course, that doesn't tell you that every day it's going to go up. It just tells you that if you believe the statistical models, which by the way are not very good, and if you were to wind back and repeat that day 10,000 times and take the average, it would have gone up. But since the latter is impossible and the first is also false, but that's the rough idea. Okay, and this thing, that's the variance, that measures actually, that's called the risk of the portfolio, right? And if you take the square root, it's the standard deviation, and it says, if I'm a portfolio manager and I wake up in the morning, have my coffee, then try to find out, you know, did Stanford's endowment go up or down today? Then I take the mean square value of that. That's going to be that is going to be the risk of the portfolio. It's called the, you know, volatility or something like that. Okay. So again, this is just so you get the idea. Okay. So this is really it's a bicriterion problem. So I've got 2 objectives, which is risk and return. Well, the return I want big and the risk I want small. So I could have done this with some sick cone that was kind of like R plus cross minus R plus or something like that. So, but the problem with that is then your head explodes I mean, it's correct, but it's hard to keep track of. So we'll just do it this way. We're going to minimize the negative return because we really want that to be high, and the variance, right? So that's the idea. Okay, that's what it looks like. And then what you could do here is you can actually just look through. You can walk through. There's a Pareto surface, right? Here, which is on, and those correspond to the non-dominated portfolios. And they actually will they'll trade off a curve that will look like this. This is a very standard curve. It's a risk-return trade-off curve, right? And and now I haven't drawn it. If I was going to do this, I would flip one side of it and all that kind of stuff. But this is the traditional way people show it, with return this way and risk this way. Okay? So that's the idea. So in this, without the flips of sign here, left is good, right? And up is good, right? And so you get something that looks like that. Yeah, it's a question.
Considered convex because the negative changes things a little bit.
This is absolutely, this is convex, right? Because here, the rule in multicriterion, if I'm minimizing, each objective has to be convex, right? So this is convex quadratic, the risk, right? And the negative return is affine. So it's convex. Cool? Okay. But yeah, do check, right? I just write these things down without saying that, but that's what it is. Okay. Anyway, so this shows you and you would describe this as the risk-return trade-off curve. And there's some, I don't know, there's even some name which I've forgotten. And I forget what this is called. This is called I don't even remember anymore, but it's got some, does someone here know the name? Anyway, it doesn't matter. It's the risk-return trade-off curve. Let's just leave it that way, okay? Or the risk-return optimal trade-off curve, right? And so this is what it looks like. And what this shows is actually so here I have 4 assets, so they add to 1. This is a stack plot, right? So a stack plot says if you, each vertical here gives you a point on the optimal risk return trade-off curve. And at this point, you've got a little bit of x1, a little bit of x2, a bunch of x3, and a bunch of x4, right? So over here, like when you insist on 0% return, you get x4. By the way, x4 is probably cash, which would have no risk, right? I don't know what x1 is, but it's probably the most risky of the assets, right? And so as you would say, I'll use the language people would use, as you take on more risk, you get a portfolio that actually at some point you stop holding any cash and you only hold this. Maybe these are like bonds or something, I don't know, right? Then you start taking on, whatever, some type, and then this would be large cap stocks, and these would be like small cap or something. I'm just making this up, but not entirely, right? So it would look something like this. So all this makes sense? So this is the picture, and you'll see variations on this sort of thing all over the place. Okay. By the way, a little bit later, I will show how you actually compute this, and for that matter, you will be doing it on your homework that's due Friday. So it's actually quite straightforward to do this. Okay. So now we're talking about scalarization, right? So scalarization it refers to taking a vector objective and then mapping it down to a single score, right? That way, that will give you a linear ordering, because when we scalarize, right, you had a production design and I had one of ours is better because it comes up to a certain number, right? Now, let's see how to do that. Well, you'll remember from a couple weeks ago, we talked about what happens if you take a vector that's positive in the dual cone, right? And you minimize lambda transpose f of x, that's guaranteed to give you a Pareto, a minimal point, which we now in this context refer to as a Pareto optimal point, okay? So it says this problem here is an ordinary convex optimization problem. And there's a whole bunch of subtleties that I'm not mentioning. Here's one. If f0 of x is k convex, that means it's a vector function, which is k convex. It's convex with respect to the cone k. If I take lambda as positive in the dual cone, then that's a scalar function. That scalar function is convex. So that's the first thing. So this is an ordinary old convex optimization problem. And the picture is pretty cool, right? It basically says, if here's O, what I do is, let me look at level curves of lambda transpose f0 of x, right? And so those are going to be basically hyperplanes in this O space. And then what you want to do is you want to go as far as you can this way, right? And in this case, you would find this point. And sure enough, it is indeed an optimal point, right? And also, a lot of other ideas come up here that you would see. You could see that right here, where this is tangent to this thing. And that roughly means, and it's got a slope that's like, -1 over lambda or something, but it basically tells you locally the trade-off between the two variables, the two objectives, right? So there's going to be, it's like an exchange rate. We'll get to that. And in fact, it is correct to think of the lambda here as a vector of prices. We'll get to that. Okay, so in some ways, this is making something very intuitive, kind of fancy, but that's okay. This doesn't bother me, right? A gazillion people see multi-criterion optimization all the time. But all they do is they just immediately do, without even saying anything, they just say, yeah, how do we solve it? And you go, we'll just throw in some weights, right? Like you're doing regularization in machine learning. And so you throw in loss plus lambda. Why is this dinging at me? There we go. You throw in loss plus lambda times your regularizer. Everybody, you've seen this, and you've seen this in lots of, and people, they don't even say anything about it, but because it's obvious and it's fine, but this is what you were doing. Okay. Now for multi-criterion problems, we can be a lot more specific about what this scalarization, this particular scalarization does, right? So what it does is, it's actually kind of cool. It basically says, here are these things that you want small. Capital F1 all the way to capital FQ. You want them all small, right? Then these are positive numbers. And we can actually literally interpret the lambdas as literally the price of that objective. That's how much you will pay. If that's 12 and that's like, whatever 10, then this is going to cost you 120 bucks. So the lambdas are literally prices here, right? And this would be like, for example, if we had two production you say, well, I know how to do, or if I'm designing a circuit and I say I want both the area to be small, the dynamic power to be small, these types of things, we would just set prices for those objectives. And then this is the total price. What's interesting there is you can change the prices and you'll get a different choice. In fact, this is what will allow you to actually move along the trade-off curve if there's two. If there's more, people call it the trade-off surface. Everybody got this? So it's all pretty straightforward, but it's kind of, it's interesting to look at. So here we go. Let's do the regularized least square. I mean, this is, here we go. Here's regularized least squares is I want this thing interpreted as a fitting error to small. And then I want also the x, which in this case we interpret as the parameters in a, let's say, a regression model. I want those to be small, right? We'll talk much more about that later. But so how do I do that? Well, I will take something that's a positive 2 vector. By the way, if I multiply that vector I can scale it by any positive number, and I'm going to get, when I solve this problem, I'm going to get this, it's just a multiple of this. So I can, without loss generality, make the first one 1. By the way, people often they often interpret the first objective, they call that their primary objective. And then in this case, you'd say, well, our training loss is the primary objective, and your secondary objective is that the parameter shouldn't be big, right? And so that gives you, and so basically gamma is a translation, it's an exchange rate that tells you how much large X irritates you compared to large residual. That's what it tells you. If it's 15, it means, I don't know, it means something, right? A lot. It depends on the units of these things, right? Oh, by the way, in many cases, it's actually very cool to think in terms of, to put the physical units in there, right? If one objective is fuel use, it might be in kilograms of fuel. Another objective could be the smoothness of the ride. It could literally be something like the RMS value of the jerk. People know what that is? Sorry. Okay, that was quasi-slang, quasi-dialect. So, in control and mechanical engineering, I think you have the position, first derivative, second derivative is acceleration, and the third is jerk. And then after that, the fourth derivative is snap. Good, snap, right? So that is just universal. So for example, when you get on a fancy modern elevator, not in this country, but if you had one that had real technology, you got a fancy one, you wouldn't even feel moving. The reason is they've actually have a trajectory that has minimized the snap. Everybody got that? Also, I think drone trajectories are designed to minimize snap. So if you minimize the snap, that's the fourth derivative. Again, this is cultural enrichment. You don't need to know this, but it's fun. And anybody know so they have 3 more derivatives, which are never used, but there's a good joke. There you go. So the crackle and pop, that's it. So you can really impress your mechanical engineering or control friends by if they're saying, what are you doing? I'm making a drone fly around the Stanford campus. And you go, cool, what are you minimizing? And they'll say, our RMS value of snap. And you go, how about crackle or pop? And you'll get a rise out of them. I mean, I assume. Okay, sorry. That was a big digression. Okay, we're back. Okay. So this is fine. Everybody knows this is just a least squares problem, and you can solve it. And everyone here has probably seen this in some context. It's ridge regression, but we'll get to that later. Okay? Yeah.
Sorry, on the previous slide there was a constraint that lambda had to be in K star, right?
That's right.
Can you explain the intuition behind that?
Oh, well, okay. First, there's the math, right? When I form this better be a scalar convex optimization problem, and when I have an objective function which is a vector and is convex with respect to a cone K, then actually if you form lambda transpose f0 of x when lambda is positive in the dual cone, that's guaranteed to be a convex function. If not, if that fails, this need not be convex. And so this is all very nice, well and good, but we can't solve it. I don't know if that counts as intuition, but anyway, yeah. And the dual of r plus to the q is r plus to the q. So basically it says, I mean, this is a way to make it, in the multicriterion case, it's making it much more fancy than it needs to be. It would basically say, take a bunch of positive weights. Minimize the positive weighted sum of the objectives, okay? And the statement is, you will get a Pareto optimal point, right? You want another one? Change the weights, right? And we'll talk about what the weights mean too. Yeah?
The last one was you can almost find all Pareto optimal points. So
sorry, I missed that.
Is that we can't find by varying lambda?
Oh, we'll get to that. So it turns out, yeah, as you vary lambda, you will get almost all Pareto optimal points. You won't get the limits, right? You will, in this problem, you would not get that dark point right there. So sorry, actually, this is a non-convex problem, so I shouldn't be using that as an example, right? So we'll get to that. Okay. All right. So I guess we looked at this. And the risk return trade-off, this shows you actually how we computed that, although there's several other ways, and I'll explain that. By the way, this has a name. If you flip the sign on this, it's p bar transpose x plus gamma this. That's actually called, so this is the return. If I flip the sign, p bar transpose x is the return, minus gamma x transpose sigma x. So that, when you do that, that's the risk. Gamma times that's called the risk adjusted return. That's just a completely standard phrase. Everybody got that? And then gamma is called the risk aversion parameter, right? Because basically because of the sign, it's, in that case, you want to maximize risk-adjusted return, and it's basically something good, which is a return, minus, that means it penalizes you to make a choice that has high risk. And gamma tells you how much risk irritates you, and it puts you on the scale of the return. So that's why it's called the risk aversion parameter. But this is not a bad thing to know. Everybody got this? By the way, there's plenty of other ways to solve this problem. I'm going to go back to that and just mention it. Because you'll be doing this on your homework. You don't have to, you could scalarize, it'll work, I guarantee it'll work. You could do another thing that would work perfectly well here. I could sweep, let's say I'm going to sweep across standard deviation of error like this, right? That's the square root of this or something, right? So what I would do is I would minimize minus p bar transpose x, and I'd put a constraint on that and sweep the constraint value. And you'd get the same thing. It basically being, I would say your risk should be less than 10%. And then you simply maximize the return, and you would get this point. And then you'd have, for risk limit in risk limits, I don't know if I'm kind of speaking roughly in Python or something, right? You'd solve the problem, and then report the return and the risk, and then you'd plot it. Everybody got that? So, okay. So you can do that, I think, I forget, it asks you to get a trade-off in some energy storage system. I think is that on the current homework? Or did I just remember that correctly? I think it is. Okay. Okay. So, all right. That finishes that. Actually, it's a perfect segue into the next topic. So the next topic is duality. It's actually really fun. I mean, it has to do with like Lagrange multipliers and stuff. And I don't mind saying that the first 2 or 3 times I saw Lagrange multipliers, I had absolutely no idea what it meant. It was taught as a behavior. And it was basically, the behavior was this. Like, take your constraints, take your objective, add to it some multiple of the constraints, and you're like, cool. And you go, what are those? Those are Lagrange multipliers. And you go, now what do? Take partial derivative and set them equal to 0. You go, but what does it mean? And they're like, shut up and just do it. I mean, that was kind of my experience of it, right? And the second time it happened, there it was again. And I was like, but what are these things? And they're like, don't worry about it, right? So anyway, good news is, I hope that by next Thursday, you will understand exactly what it means. Or at least this is the first time I ever understood it, was in the context of convex optimization. Okay, so let's look at this. And it starts slowly. It just very innocently goes step by step, and you'll see after a while we start saying things that are not remotely obvious. Okay, so okay, here it is. So we'll start with the Lagrangian. Oh, by the way, this strongly suggests that this is not a new development, right? Because Lagrange was doing this around 1820 or 1810 or something like that, or maybe even earlier. I can't remember. Anyway, so now the truth is, he would recognize like baby versions of it. And so this is just an honorary thing where it's attributed, it's called the Lagrangian, and I don't know. So, and it didn't have inequality constraints then, but whatever, it's just an honorary thing. Okay, so here's what it is. So you have this standard form problem. And by the way, a lot of the interesting applications, the problem is not convex. Okay, so just I have a standard form problem. And now I'm just going to form the Lagrangian. And the Lagrangian is going to be this. It's actually super interesting. It goes like this. It's a single function. It's going to be the objective plus a weighted sum of the constraints plus this inequality constraints plus a weighted sum of the equality constraints. Okay? That's the Lagrangian, right? And okay, that's the idea. And it's kind of, then people would give ideas like this. Oh, so one way to say it is you would say, this is like a planned economy or something, right? This says these are just rules and regulations. Like if you violate this or this, then somebody in law enforcement or the SEC is going to come after you. That's like a plan. It's a requirement, right? Then you'd say, oh well, this is like the market version, right? And by the way, all of this will become a little bit more precise later. And the market version says, well, you know what? You want to violate that inequality? Okay, that's fine. And if lambda is positive, it just says you're going to pay for it, right? That's what it says. So that's the idea, right? Also, let me just draw a picture to show you actually how appallingly naive this looks, right? So because it's very weird. So I'm just going to draw. Let's have a problem. This is 0, and this is going to be f1 of x, right? This is just f1 of x, and I'm going to have an objective, so I'm going to plot f0 of x here, right? Okay. So here, if you propose to me an x, we will evaluate f0 and f1. And the semantics of an optimization problem is if you're over here, it's completely unacceptable because you violate the constraint because f1 of x is positive, right? So this is unacceptable, right? If you're on the left side, everything is cool and you want to go as low as possible, right? In fact, that's the semantics of an optimization problem. Everybody got this? So roughly speaking, you're saying, here's how I care. I could make it an unconstrained problem by just writing it this way. The indicator function of f1 of x is less than 0. So this is 0 if this predicate evaluates to true, and this is infinity if this is violated. Okay? And so solving the constraint problem is the same as minimizing this function, right? Everybody see that? I mean, it's kind of silly, but that's what, everybody got it? Okay, so I'm going to draw the indicator function. It looks like this. So someone says, what are you doing? And you say, well, I'm converting my constrained problem to one that's unconstrained by putting the second term, which handles the objective. And it's a weird term. It's like a weird emotional, it's like a bipolar. It's either like 0 or plus infinity, right? So it's just like, okay, that's fine. So basically, that's this picture here. Okay, now let's look at the Lagrangian. Well, the Lagrangian is going to be f0 of x plus lambda f1 of x. Okay, so, right, that's the Lagrangian. I'm going to draw that. Okay, here, looks like this, right? That's lambda, right? Right, that slope is lambda, okay? So, and now you could see, and by the way, if the story starts, like, I want to develop methods that handle constraints, but using just like, using unconstrained optimization. And the first thing someone does is says, yeah, no problem. You see this thing? I'm going to approximate it by that. You would say, that is not a very good approximation. Like, everybody agree? It's ridiculous. So I'm just saying that the whole beginning to this story is appalling. It just doesn't make any sense. Like, that curve, that line, is not a good approximation of the true one. Also, it shows you all sorts of weird differences, right? Like in the true optimization problem, if you have like a warehouse usage limit, so this is how much your f1 of x is how much you're above your limit in using warehouse space, then basically it says you go above the limit, totally unacceptable. If you're below, I don't care. You could be using all of your warehouse, or you can come in over here, which is like you got a bunch of warehouses, you're not even using it. You see what I'm saying? And guess what? In the optimization problem, there's nothing different about them. This one has a super interesting interpretation. It's a price. Because presumably F0 is in like US dollars or something like that, right? And what this says is, yeah, you want to go over your maximum? No problem. You want to operate over here? Go ahead. This says you're going to pay for extra warehouse space. Everybody got that? But then there's also a flip side, which is over here. You will be subsidized for having extra. You can rent out warehouse space you're not using and actually generate income, right? So it's really quite different. Everybody see this? These are not, this is just to kind of give you the idea of how all this is going to go together. But these are the ideas. They're very basic. Everybody got this? Okay, so it's the idea, and people would blabber about, a market economy versus a planned economy and so on and so forth. But, this is kind of the idea. Oh, also, that strongly hints these weights, these Lagrange multipliers, they're going to, in many cases, turn out to be prices. Okay? So that's what they're going to be. Okay. So now, and this gets very weird, but it's like this. You'd say, okay, let's take this Lagrangian, which is sort of an attempt to basically handle the constraints for a problem in the objective, right? But you're doing it in a weird price-directed way. You're just saying there's a price for each of these things, and you can violate them, blah, blah, blah. So it looks like that. Okay. Now, what we're going to do is we're going to define the dual function, and it's going to be a function of these Lagrange multipliers. They're also called dual variables. By the way, they're also called all sorts in many application areas. They have specific names in that application area, right? Like in many they're called shadow prices, right? Or for example, in energy they're called locational marginal prices is what they're called, right? So in a lot of fields, these things just have names, right? Okay, and so this thing is the least cost here over all your choices with these Lagrange multipliers, which we'll later see interpreted as prices. So you minimize that, and whatever the minimum is, that's called this dual function. You saw something like that. It was a conjugate function. If you remember that one interpretation of a conjugate function was one is you interpreted y as a vector of prices, and then the conjugate function was the optimal cost, the minimal cost as a function of the prices. I don't know if you remember that interpretation. This is exactly that. If you think of these as prices, which you will shortly, then basically the dual function is the optimal cost as a function of the prices, right? So everybody, okay. Now we're going to make some extremely simple observations, right? The first is this. The first one is this function g is concave. The dual function is concave, even when the original problem is not convex. It's just concave. Actually, somebody want to explain why? Why is g concave?
Minimum of convex functions.
Yeah, it's a minimum of affine functions which promote to convex. Yeah. So this, if you look at the Lagrangian, it is an affine function of lambda and nu. If you consider lambda and nu the variables, it's an affine function. Now, it might be really complicated because I don't, that's for any particular value of x. It's an affine function. This says just take the infimum or minimum over a family of affine functions. That's concave, period. Okay? So the first one is this thing is concave no matter what. Always, just period. Okay? Second one is weird, and it looks very deep and all that kind of stuff, and you will soon see stunningly non-obvious consequences come out of it. But it just says this. It says as long as the Lagrange multipliers associated with the inequality constraints are non-negative, then it says that g of lambda and nu is less than p star. Okay, so why would that be? Well, suppose x tilde is feasible. If x tilde is feasible, then fi of x tilde, these things are all non-positive, right? These are all 0. So if x tilde is feasible, then this term just goes away. The lambda i's, I'm going to assume, are the prices are non-negative. The fi of x are less than or equal to 0 because it's feasible, right? So this term is less than or equal to 0. Everybody, by the way, I'm using extremely deep mathematics here. Basically, the fact that the product of a non-negative number and a non-positive number is non-positive, and that when you sum non-positive numbers, you get something that's non-positive, right? Oh, and one more deep fact. If you take a number and you add a non-positive number to it, it's less than the original number. Okay? So I'm just saying there's nothing deep yet. I will tell you when we get to the deep part. Right? So, but this wasn't it. Okay. And that says that if you had any feasible, if x tilde is feasible, then the Lagrangian is less than or equal to f0 of x, the objective, right? Now, therefore, if you minimize over that, you're going to get something that's a lower bound. So you get g of lambda and nu is actually a lower bound on the optimal value of your problem. Okay? So everybody got that? Again, it's not yeah?
The same property holds for mu, right? As well as lambda?
I missed that. What was that?
This property also holds for mu in addition to lambda, right? Like there's nothing special about lambda in this case?
No. What's required is that the Lagrange multipliers associated with the inequality constraints have to be non-negative. By the way, it makes perfect sense over here, right? Because while this is not a good approximation here, I mean, it's not a good approximation, right? But what if someone came up to you and they said, "Oh yeah, I can handle that for you. Yeah, your warehouse space. Yeah, I'm going to approximate this function by that." Now, that's weird, because what this says is, this basically says, I'll pay you in fact, I'll pay you more and more to violate your warehouse space limit. That's what it says. Oh, and by the way, if you actually satisfy the constraint, I'm going to start charging you. I mean, so the other one was merely a bad approximation. This one is appallingly stupid. Okay, so I'm just saying if you wanted a quick interpretation of why lambda has to be bigger than or equal to 0 here, is that this doesn't even make sense, right? Actually, if you think about it, it's like it's a scalarization with a negative number in there or something like that, right?
Sorry, I didn't mean that lambda can be less than 0. What I meant is that it's also the case that if mu is greater than or equal to 0, then g of lambda nu is less or equal to 0.
That's true, but in fact, it's a stronger statement. There are no conditions on nu whatsoever. Could be negative, could be positive, doesn't matter. What you said is a strength. You said, yeah, but if nu is non-negative. You go, well, yeah, I agree. And we'll see a lot of times, we'll get to it. It'll be interesting when nu, so the point is, there's no constraint on nu. Nu could be negative or positive, right? Yeah?
Is there a similar intuition behind nu, like in terms of, yeah, because like, I feel like
there is.
Draw the same.
Yeah. I will show you what it is, okay? Yeah, what's the interpretation for this? So let's do, what are the names of their H? Is H the name of our, yeah. So let's do this. Okay, so it looks like that. This is now going to be H1, right? And now I'm going to draw the true, the true object. So the true objective is this. If H1 is 0, it's cool. You're satisfying your equality constraint and you get a 0. Outside that, it's out here. This is plus infinity. Everybody agree? So it's a function that kind of looks like super big, goes down to 0 if you're 0, and then goes back up again, right? Okay. Now, what this says is I'm going to approximate that with a linear function. I mean, it's appallingly bad approximation, but it's saying something like this, right? So that's a bad approximation, but so is that one, and they're all kind of they're all a little bit they're similar, right? So anyway, this is the picture for that. Does that make sense?
Yeah, but it still kind of says that like we can just like increase it in some directions, like make it smaller and smaller, right?
We'll get to that. Actually, my point about this approximation is that when I explain it this way, it doesn't look like a good it doesn't look like a story that starts this way. When someone walks up to you and says, yeah, no problem, I have this thing that looks like this, or this even worse, this thing that looks like this jumps down to 0. And I go, I'm going to approximate it with a line. A normal person would say, dude, that's a terrible approximation. Like, that story is not going to end well, right? Everybody, I mean, if someone told me that, it would be ridiculous, right? But obviously, the story is going to end well, or I wouldn't be telling it to you, right? But the point is, it's shocking, right, when someone first says what it is, right? So I guess that's my so I haven't said it's obvious. In fact, to me, right now, the intuition should be, this is ridiculous. It's completely ridiculous. How could anything good come of such a crappy approximation, right?
I mean, like, at least with lambda, we say it has to be positive, so it's always like an additional cost. And that's what makes it like less intuitive for this one.
I think I'm saying this looks, when I describe it this way, it sounds like a really bad idea. Okay? I totally admit that, right? So, okay, fine. Let's look at some examples to see how this works. Yeah?
Who's the bar in the previous, the x bar?
X tilde? Oh, this just says, suppose x tilde is anything that's feasible for the original problem, right?
Oh, okay.
Right. Then what we're doing is showing that the objective for x tilde is bigger than that, right? But x tilde was anything. So if you pick, for example, an optimal point for the original problem, this would be p star, and that would be g, and that would be this constraint here. Sorry, inequality, right? Cool. Okay. All right. Okay, let's look at some examples. So here's one. Minimize the sum of squares of a vector subject to ax equals b. It's like a least norm or something like that problem. And there's an analytical solution. So this is silly, but just to see how this works, right? So here's what we do: is we form the Lagrangian. So that's the objective plus nu transpose. That's an equality constraint. Nu transpose ax minus b. That's the violation, right? This is a convex quadratic function. We minimize that to get the dual function. To minimize that, you just set the gradient equal to 0. It's a set of linear equations, and you get x is that, okay? Now I plug this x back into L, that's the Lagrangian, to find what g of nu is. And when I do that, I get g of nu is this thing here. And I'm not going over the algebra, but it's not much. And sure enough, look at that. That is concave. Why? Because this is convex. AA transpose is convex here. Is positive semi-definite. This is convex with the minus sign. It's going to be concave, right? So sure enough, that's good. I mean, we knew it had to be, right? But now, what's interesting about that is it says, if you wanted to solve this problem, then it says immediately, if you pick any vector nu at all, and you evaluate that function, that is a lower bound on this problem. Okay? I don't know. Let's try some. Here's one. Nu equals 0. What's the lower bound on this problem? If I take nu equals 0, what lower bound do I get? 0. Okay. So then I say to you, oh, wow, yeah, thanks for showing me your problem. I can tell you this. You ready for this? By duality, I can tell you this optimal value could never be negative. And people would look at you like you're an idiot because, of course, the objective is like non-negative. Okay, everybody see what I'm saying? Okay. So, okay. Let's see. Okay, so that's the lower bound. Anyway, that's the idea. So, but this actually already has weird applications, right? Because you could have some gigantic problem like this. We could solve it analytically, but you have some quick heuristic to do it. I mean, it could have a billion variables, and you have some quick heuristic to do it. And then you could just ask yourself, how far am I from optimal? And you would just calculate this bound. You'd have to find a good choice of nu, and you get a lower bound. You go, I'm 5% optimal, and you're like, totally cool, because our original problem, nothing there was accurate to more than 5% anyway, right? So we'll get to that. There are going to be a lot of applications of this, which we'll get to shortly. Okay. Now it's going to be not obvious. So let's do standard form linear program. So here, I want to minimize this linear function subject to equality constraints and a non-negativity on x. So my Lagrangian is this. It's the objective plus equality constraints interproducted with this Lagrange multiplier nu, right? And then I'm going to rewrite this silently as minus x less than or equal to 0. So it's in our standard form. And then you get minus lambda transpose x. And so this is the Lagrangian. What kind of function of x is this function? What is it? It's affine, right? So to find g, we have to minimize that function over x, right? What's the minimum of an affine function? What? Yeah, it's minus infinity. Usually. There is one exception. How could the minimum of an affine function not be minus infinity? How?
Restricted on the domain.
No, I'm not talking about restricted on the domain. I'm just having an ordinary old affine function. Here's my affine function. It's let's go, P transpose x plus q. There's my affine function. I'd like to minimize that over x, and I'd like to know what the minimum is. Well, it's usually minus infinity, right? But there's one case where it's not. If p is 0, which means that if the linear part vanishes, then what is this thing? So I would write something like this. Inf over x of this, of this is going to equal, mostly it's going to be minus infinity. But here it's going to be q, and that's if p equals 0. Okay? Everybody got that? So that was a pretty quick calculation there. And then that's what we have over here. So when I minimize this Lagrangian over x to get g, that's the dual function, I minimize this, and basically what happens is, if this is non-zero, the minimum is minus infinity. Otherwise, I assume this is 0, and it's equal to that thing. So this is what I get. Okay? Okay. So g is, in fact, it's a linear function restricted to a hyperplane. That's not a hyperplane, an affine set. That is, in fact, a concave function, right? I mean, it kind of has to be, right? And you know what this says? I'm going to rewrite this. This says that A transpose nu minus lambda plus c is 0. That means A transpose nu plus c equals lambda. Lambda is anything is any parameter that's bigger than or equal to 0. And then I get this lower bound property. It says this. It says, you look at this linear program, and it says, yeah, you know what? The optimal value of this thing is bigger than or equal to minus B transpose nu. For any nu that satisfies A transpose nu plus C is bigger than or equal to 0. Okay? Everybody? And that just came straight from the dual function. Now, it turns out for a lot of these, you can just show it directly, and it's not hard. I mean, I could let me do it for that one, and then I don't think I'll ever do it again, but I'll do it for that one. Let's do that. So my original problem is minimize C transpose X, and then subject to, I think it's AX equals B, and X is bigger than 0, right? And then the claim is, if somebody walks up to me on the street and says, I have a vector nu, and A transpose nu plus C is bigger than 0, they claim then, this implies that minus B transpose, sorry, I have to look at it over here, nu, is a lower bound on P star. Okay? So this is pretty cool, right? So that's what it says, right? Now, if we just asked, so you came up to someone on the street, or now if we put that on a homework, you couldn't do that. It's like, how would you show that? It looks very deep, but in fact, it used absolutely nothing but the completely trivial steps I had before. So this we can show, let's just show this directly just for fun, right? So here's what we're going to do. Suppose x is feasible. Any x is feasible. That means ax equals b, x is bigger than or equal to 0. Okay. Now, if that's the case, then let me look at this nu transpose. Then this must be true, right? Because x is feasible, so ax equals b. So this surely holds, right? Oh, and I'm assuming somebody came up with a nu that satisfies this. Everybody agree with that? I mean, you kind of have to, right? It's like simple stuff. Okay. But then I'm going to write this thing. This says that A transpose, here, this is A transpose nu plus C is bigger than or equal to 0. We agree with that, right? Now, X is also bigger than 0, right? And now I'm going to use an extremely deep fact. Inner product of two non-negative vectors is non-negative. Okay, so we kind of, right? Again, it's just not hard, right? So I'll put, I'll put this on the other side. So I'll write nu transpose A, and I'll multiply, let's see, plus C transpose X. That's bigger than or equal to 0, right? Everyone agrees with that. And I'm just using the fact that that's an inner product of two non-negative vectors. So you have this, okay? Expand this out. You get nu transpose AX plus C transpose X is bigger than 0. But wait a minute. This thing is equal to nu transpose B, right? So this is nu transpose B. And then I put this over here, and I have minus nu transpose B, and I get this. So here's what I just showed you. I said, take any X that's feasible for this linear program. And what I showed you is, I don't know what C transpose X is, but I'll tell you one thing about it. It cannot be smaller than minus nu transpose B. So everyone see that I just completely derived it from scratch with none of this Lagrangian and blah, 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 and dual function. Everybody see it? So, okay. So that's how that goes. Okay, so now this is already kind of interesting. As a matter of fact, later, here's what you're going to find. It's pretty awesome. When we do numerical solution of an LP, here's what's going to happen. When you solve that LP, you will get X back. Whether you like it or not, you're also going to get a nu. Right? And this is going to be true for most, all the convex problems you solve. And which is amazing, right? Because you're going to get a nu and the bound is going to be tight. So it's going to be so what's going to happen? So your model of a solver is going to look like this. Here's my problem. And they go, no problem. They say, here's X, right? You check as feasible and its objective value is like 3.7. Everybody following this? Okay. You will also be given what's called a dual certificate. A dual certificate is it'll give you dual variables, which if you evaluate the dual objective, which is G, you would get a lower bound on the optimal value. Everybody following this? When you evaluate it, it's actually equal to the value the primal value you were given, right? The objective value. Everybody see this? That's called a dual certificate. So it means you don't even have to trust the solver. It basically, abstractly, I think it's beautiful. It actually returns two things: an optimal point and a very short self-contained proof that no one could do better. Everybody got it? That's what a dual certificate is. We'll talk much more about this later, but it's super interesting, right? Is this making sense? Vaguely? Okay. Here's one. We can do equality constrained minimization. So here I just have a general norm, right? So I'm going to minimize a norm subject to AX equals B. This is the Lagrangian. I take the norm minus, and then I have nu transpose times AX minus B, or in this case I wrote it as B minus AX, and I get this thing, right? And then we have to minimize this. Now, by the way, if you look at this, you'll already see something clear. B transpose nu has nothing to do with X, so that comes out of the infimum here. But here, this is a norm minus a linear function. That's the conjugate, actually. That's the conjugate function. So what happens? And you can also work out what that is, right? That the norm minus a linear function, when I minimize that, I either get 0 or I get minus infinity, right? And so here you would get this thing. And again, I'm not going over the details. I would let you do that, but that you get something like that. So the dual function is this linear function B transpose nu, provided A transpose nu in the dual norm is less than 1. Right? So that's what you get. Then it says this. You want to solve this problem? Then here's a lower bound. It says a lower bound is B transpose nu for any nu that satisfies this. Right? in the dual norm, right? So let's suppose this is a minimum fuel trajectory generation problem, and you want to take a satellite from where it is to where it is supposed to be, and you want to use minimum fuel. This would probably be something like an L1 norm, okay? That's your job. You work this out, and what's cool is this says, I can give, if I take any vector at all, and it satisfies this, then if I evaluate B transpose nu, that's a lower bound on the minimum amount of fuel it's going to take you to get from where you are to where you're supposed to be. Everybody got this? So it's already getting kind of interesting. And there should be at least very strong hints that a lot of this is unbelievably useful. So everybody got this? So this is not obvious, right? These things are not obvious. I could give just a simple proof directly that this is a lower bound and so on. Now it's about to get even more interesting, because we're going to look at a problem. Well, it'll come up again. So it's two-way partitioning. So this is the two-way partitioning problem. I have a set of n objects, and I want to partition them into two groups, right? And the way I'll do that is I'll encode it with a vector x that has +1. If xi equals +1 means, item I is in the first group. Xi equals -1 if you're in the second group. Everybody got it? So that's the pic. So that's what this says. That says that each x is either plus or minus 1. And then my objective is this thing. And to get a rough idea, we should actually say what x transpose wx is. It's because it's an interesting problem, and maybe you've seen it in some other class or something like that. But it's worth saying what it is. Is it x transpose wx? Yeah. Okay. So it's x transpose wx, but that's equal to this. It's the sum over I and j of wij xi xj. I mean, so we all agree with that. That's a quadratic form. Now, xi and xj are each plus or minus 1. So this product is +1 if items I and j are in the same group, and it's -1 if they're in different groups, right? And so this is equal to the sum of the w's when they're in the same group minus the sum of w's when they're in different groups, right? That's what this says. And so you should interpret, what are we doing? Are we maximizing or minimizing? We are minimizing. So if we're minimizing this, it basically says wi is the cost of having, let's say we're going to split a group of people into two groups, right? So this says if wij is the cost of having person I and person j in the same team, if we're making two teams. Everybody got this? So if wij is positive, it means they don't like each other. If it's negative, that's totally cool. It means there's a strong affinity and we would like them to be in the same group. Everybody got it? Right. And the same is true for basically you have an equal and opposite charge, right? So if you say if wij is +3, it means you will pay 3 if you assign I and j to the same group. And you will have a revenue or income of 3 because it'll become -3 if it's -3, it's the other way around, right? So the w's specify how we like, how much it irritates us to have items in the same group or different groups, okay? So, okay. So this is the problem. Okay. So let's look at the dual function. Oh, it's obviously non-convex for two reasons. W need not be positive semi-definite. We didn't say that it was. Okay. Reason 2 is we got a big old fail right there, right? Because we have squares equal to 1, right? By the way, if I take xi squared less than or equal to 1, that's convex if W is positive semi-definite, right? So, but okay. So we take the dual function is we take the objective, right? Plus, and then I just simply add up nu I times these xi squared minus 1. And what I end up with is a quadratic function, a quadratic form in x plus a constant. Okay? And now we're going to have our quadratic form minimization. Earlier today we had our how do you minimize an affine function conversation. Now we're going to have a quadratic form minimization conversation, right? So if you minimize a quadratic form, what do you get? Someone walks up to the street and says, here's my X transpose, whatever, not W, but X transpose, AX. A is symmetric. What's the minimum of that? Well, if that matrix has a negative, it's got real eigenvalues, symmetric, right? If that matrix has a negative eigenvalue, that minimum is for sure minus infinity. Because you sail out along find a negative eigenvalue. But for that matter, just find a point where the quadratic form is negative, right? If you just go out farther and farther, it'll get more and more negative. In fact, quadratically so. So then the minimum is minus infinity. Everybody got it? But if that matrix is positive semi-definite, and I ask what's the minimum, the answer is real simple. It's 0. Because you could take 0 as your x equals 0, but because it's positive semi-definite, you can't get it, it can't be anything less than that, so that's it, right? Everybody follow that? So G is this function. It's minus 1 transpose nu, provided W plus diag of nu is bigger than or equal to 0. That's in a symmetric matrix sense, right? Okay. And the lower bound property says, you see this problem here? You know what? Here's a bound on its objective. That's a lower bound on its objective. It's minus 1 transpose nu, for any nu you can find that satisfies this. Okay? So that's what that says, right? And it turns out you can get all sorts of famous bounds out of this by just plugging numbers in. But that's the idea. And this is related to spectral partitioning. How many people have seen that? Ooh, just a hand. Ooh, I'm sorry. Everybody needs to know about spectral partitioning, right? You're not going to be able to do any kind of any serious street fighting applied math if you don't know about that, right? Because partitioning problems come up all the time, and you need to know about it. I'll just show you quickly what it is here, just for fun. I won't go into the details, but it's actually weirdly another. Let me just explain it very quickly. So and I won't go into the. I'll give a very simple version of it, right? So you have this thing, and then subject. Then we're going to minimize this thing, subject to xi squared equals 1. That's not convex, right? But if this is true, if xi squared is 1, then everyone here would have to, I would hope, agree that that's the case, right? Now, by the way, this is a relaxation, right? Because if the former constraint holds, then this one has to. Okay, W symmetric. Anybody take a look at that? You know how to solve that problem? First of all, is it convex? Is that convex? No. So this, because of this, right? If that was less than or equal to, it'd be convex, right? But this is not convex, okay? This is one of the, there's about 7 problems we can solve that are not convex. This is one of them. It's just an eigenvalue problem, right? What's the solution of this? In terms of the eigenvectors. What's that?
The smallest one?
Yeah, we know how to do this. You find the smallest eigenvalue of W, you find its associated eigenvector, and you scale it by n. And that's literally the solution, right? That's not a heuristic or anything like that. So anyway, oh, by the way, when you do that, what have I done here? My God. Okay. When you do that, you get something really interesting. First of all, you get a number, because this is a relaxation. That's a lower bound on the original problem. But then you also get this. I get an x's which are all, they satisfy this, but they're definitely not all plus minus 1. Somebody want to make a suggestion to make a heuristic assignment at that point? You have a vector, they're all floats. Some of their squares is n. But the original problem, you wanted all the xi's to be plus or minus 1. Someone please make a suggestion. Round them. Done. Take the sign. Done. Congratulations. That is spectral partitioning, except for one thing I didn't tell you about, which is we can adjust the diagonal of W in a way that will make that slightly better. That's spectral partitioning, right? This works for gigantic problems. It works super well. So there you go. Yeah?
So in this problem, W has
to be symmetric or positive
Oh,
semi-definite?
no. In this problem, well, okay, non-symmetric doesn't even make sense, although because you just replace W with its quadratic part. I mean, sorry, its symmetric part, right? If I have a quadratic form and I replace the matrix non-symmetric, I just replace that matrix with that matrix plus its transpose divided by 2, number one. Then, does it have to be positive semi-definite? Absolutely not. We know this problem we can solve completely as long as W is symmetric. This can have negative eigenvalues, positive eigenvalues, couldn't care less. The solution to this is X is a scaled version of the minimizing eigenvector, right? Is that okay? I think we'll quit here. It's already getting kind of interesting, and we'll keep going on Thursday.